Our presentation today features the California Department of Transportation's 2017 emergency replacement of the Pfeiffer Canyon Bridge on Highway 1 near Big Sur in Monterey County. We'd like to thank Tom Ostrom and Dory Mellon with Caltrans for coordinating this presentation. We're pleased to welcome our presenters, Ruth Fernandes, Acting State Bridge Engineer with Caltrans, Neil Weller, Bridge Construction Engineer, and David Galarza, Structures Representative, both also with Caltrans. Ruth?
Thanks, Mary Lou. This is Ruth Fernandes, Acting State Bridge Engineer at Caltrans. First, I'd like to thank the ABC-UTC for providing Caltrans the opportunity to share one of our more unique and exciting ABC projects with the national bridge engineering community. Today's webinar will be on the Pfeiffer Canyon Bridge Emergency Replacement Project located on Scenic Highway 1. This emergency project gave Caltrans the opportunity to use the ABC method of longitudinal launching for the first time in California. Now I'd like to turn the webinar over to our presenters, Neil Weller and David Galarza of Caltrans Structure Construction and Jason Wilcox of Caltrans Materials Engineering and Testing.
Thank you, Ruth. My name is Neil Weller. I'm with Caltrans, and I'd like to begin our presentation. So this is on the Pfeiffer Canyon Bridge Emergency Replacement Project. It began in February of 2017, and the completion of it was October of 2017 of the same year. Give you a brief overview of the location. It's in California on the Scenic Highway 1, located between Monterey and San Luis Obispo near the Big Sur community. Some points of interest along this route are the location itself, Pfeiffer Canyon, which is near Big Sur, just south of Monterey and Carmel. Some other areas I'll point out is Cow Cliffs, which is located to the south, Paul Slide, and also Mud Creek. So timeline of events for this project. The initial incident was discovered on February 11th of 2017. It was discovered by a hiker that was underneath the bridge, which notified California State Parks and Caltrans, which we ended up closing the bridge on Saturday of February 11th. February 13th and 15th of the following week, we had controlled evacuations from the south. Later that week, we had large rain events that caused the landslide underneath the bridge to further displace the Bent 3 column. February 21st, which was a week later, the bridge was closed indefinitely. March 3rd, the girder fabrication order was placed. Approximately mid-March, we began demolition of the existing bridge. Approximately mid-April, or end of April, we began foundation construction on abutment 2, which is to the north. Beginning of May, Highway 1 was permanently closed from the south at the Mud Creek site. And if you're familiar with this location, we had a fairly large landslide that occurred on May 20th, which closed Highway 1 from the south approximately over a year to a year and a half. End of July, we received our first girder delivery to the site. At the end of August, we began our bridge launch. In mid-October, the bridge was open to traffic. So to go do a summary of the cost, the contract and the cost. So the delivery method for this contract was a Caltrans Emergency Director's Order. It was an emergency force account contract. The authorized amount was $24 million. The actual cost at completion was $21.7 million. The contractor that Caltrans selected was Golden State Bridge out of Benicia. The scope of work included demolition of existing failed bridge, construction of the new Pfeiffer Canyon Bridge, reconstruction of the roadway surfaces and conforms, and complete the restoration work. The existing bridge was a 3-span, 3-cell, continuously reinforced concrete girder bridge. Vents were founded on a single 6 6-foot diameter reinforced concrete pile shafts. The abutments were seat types abutments founded on spread footings. Overall length of the bridge was 317 feet long. Overall width was approximately 34 feet. The traffic configuration was 1 northbound and 1 southbound lane with approximately 2-foot shoulders. So as stated before, the incident occurred, was discovered on Saturday, February 11th. We were able to get to the site on February 12th to perform initial investigations. As you can see from the photos, where my pointer is now, that's bent 2. The nearest column is bent 3, and as you can see, it is slightly displaced going downhill. When we came on site, we also discovered that there are cracks in the adjacent abutment slope. This was down at Cow Cliffs, which I pointed out earlier. The road was closed down at this location due to a rock slide and large boulders blocking the road. And I'll tell you why this is important. Pfeiffer Canyon Bridge was closed to the north. The road was closed to the south at Cow Cliffs, so approximately a 30-mile stretch of Highway 1 was essentially landlocked. There was no way in or out. You have a large mountain range on your easterly side and the Pacific Ocean to the westerly side. We came to the site and did some investigations, and we decided to allow controlled evacuations, to allow residents and also guests. There are numerous hotels located in this 30-mile stretch to evacuate the area so they can go get some supplies or just go home. We allowed approximately 3 controlled evacuations. We did 1 on Monday. We did 2 on the following Wednesday after the bridge closure. We did continuously monitoring of the bridge, the column, the deck, monitoring for deflections, displacements, and the bridge actually performed fairly well. The reason we did the last evacuation on Wednesday was because of an impending rain event that was forecasted to come Thursday through the following Monday. I believe the area received upwards of 4 inches of rain. And as you can see, we had the initial photo of this crack, but now it's growing. So the landslide is mobilized even further. Also, you can see right here, there's obvious deflection in the deck itself, and also the girder or the column support was further displaced. At this point, we closed the bridge permanently. Here are some more photos of the actual damage from the landslide displacing the column. As you can see in the soffit, there's cracks, and also cracks in at the column soffit interface. This photo is from the southern side. So here's bent 2, and then bent 3 is in the foreground, and you can see displacement. Here's a video of underneath at abutment 4. And this video was shot approximately mid-March, and it shows lots of displacement in the hillside, and then as we sweep to the left, you'll see the column being further displaced. And here are some more photos for that. The bridge never did end up collapsing on its own. We did have to demolish it, but this was the bridge in its final state prior to demolition. Since we knew we had to replace this bridge, Caltrans formed a team to assess the site and come up with a plan. We ruled out conventional methods of construction, such as reinforced concrete or stressed concrete. This due to temporary supports being in an active landslide. If you see to the right side of your screen here, this is the area where the active slide was. There was no evidence of sliding on the left side, so we wanted to keep any type of supports out from the left side of the bridge. We went with steel because we could go in shorter segments. The route from the north is fairly narrow, 2-lane road. We felt comfortable being able to navigate 60-foot long girders down the road. the one thing we had to eliminate were supports in the slides, so we decided to go with a launch method, which would go over the slide area. The initial design was a hybrid girder with a 70 KSI steel flanges. After investigation, finding out that material procurement may be an issue, we came up with two designs. So we had a hybrid option with 70 KSI steel and an all 50 KSI steel. So the final design was 315-foot single span bridge, a spanning canyon in the slide area. The girders were 50 KSI steel composite welded steel, approximately 14 feet tall. The webs were 1.25 inches thick, and the thickest flange was 4 inches. Bridge had 3 girder lines that consisted of, let me get to the typical cross section here. 3 girder lines that consisted of 5 segments, roughly 60 feet in length. If you notice, the old bridge alignment was on a radius. The new bridge alignment is now on a tangent. You can see that here, old bridge, new bridge. And that was to accommodate the launch. In addition to the final design, we did provide 2 different designs. The 70 KSI steel design had the webs in the top flange being 50 KSI steel, and the last 2 segments was all 50 KSI steel to the low moment regions, and the middle 3 segments, bottom flange, were 70 KSI steel. As I stated before, we went with the all 50 KSI steel design. To give you some perspective, the largest bottom flange plate for the hybrid option was 2 3/4 inch thick by 42 inches wide, as opposed to the 50 KSI steel was 4 inches thick to 50 inches wide. Girders were also designed with unstiffened webs at 1.25 inches. And the reason we did this was to simplify and speed up the fabrication process. So you'll notice there's no transverse web stiffeners. Things we changed in design were to accommodate the launch process, the bottom flange had to be flush. And this was so they can roll over the rollers. So what that ended up creating was a variable depth web. Another thing that we did was the bottom splice plates. We had in 3 sections, and we eliminated the middle section of the splice plate to accommodate the rollers. These were later installed after the launch was complete. And you'll see that here, middle section omitted, and you can see that's completely flush. Now I'll hand it over to Jason Wilcox.
Thank you very much, Neil. Good morning, everybody. Now, to give a quick recap, the timeline, the deflected column was found February 11th, and by February 28th, there was a set of check plans for fabricators to bid on. On March 1st, 2017, a request for proposal was sent with the check plans to the 6 fabricators thought able to perform the work, as you can see on the left row of this slide. Estimates were to include 1, the fabrication start time, 2, the delivery start time, 3, delivery end time, and then 4, cost per pound for each of the following options. First being a 3-line hybrid grade 50, grade 70 high-performing steel option. Second being the 3-line all grade 50 option, and then anything else the fabricator could come up with. The weathering steel was excluded because the project is just under a mile away, about 9/10 of a mile away. So the request for proposal were due 41 hours later on March 3rd at 10 a.m. Caltrans construction design met myself, and then the contractor Golden State Bridge met at 1 o'clock that same day to go over the estimates. And from the outset, it was agreed that schedule was the driving force, and delivery start time, and end dates were weighed heavily. As Neil said earlier, a primary concern was the availability of steel and the grades and sizes required by the design, which we learned was between 8 and 12 weeks. So what this slide captures are the proposals and rankings. Looking solely at delivery start time, we gave a ranking of 1 to the joint venture of FOT Utah Pacific for their 4-girder grade 50 line. They said they could begin delivery on May 8th. That jumped off the page. Everybody agreed this would be a ranking 1, but due to time constraints, it was agreed that our design would have to actually go back and do a redesign, check their proposal, and that just took more time than everybody was willing to allow. So the next best option was XKT's all-grade 50 option. You can see their delivery start time is June 15th, delivery end time around August 30th, with a total cost per pound of about $1.16. So this seemed to be the best option and the least expensive at this point. This did not include paint, by the way. If it was to include paint, it would bump it up to about $1.47 a pound. So it was still one of the least expensive. The third option was Vigor, with a quick turnaround time starting on June 26th and ending on June 30th. And we were discussing the merits of that when it was realized and noticed that XKT had submitted a revised proposal that came in just before the deadline. And in that proposal, there's the cost. And in the proposal, they said that they spoke with a Nucor mill, and they said that for an extra $457,000 about, they could expedite the delivery, and their delivery start date for the girders would be April 15th. So we were discussing, this was being discussed, me and a coworker, we reached out to the owner of XKT to confirm that this was even an option, and they said that they would be willing to sign a contract to this effect immediately. So within 10 minutes of finding the revised estimate, XKT was chosen. To add to this timeline, so this decision was made on March 1st, and on March 3rd, as Neil said, orders for steel started to be placed out, and by March 8th, about 800 tons of steel was ordered. By March 11th, Nucor began rolling steel that was not already available, and by March 17th, the first plates arrived at XKT. And because of the speed of the project and shop drawing review and revision times, had to hold off just a little bit, but on April 4th, the first girder web plates were being cut. Here, in this slide, you can see some of the girders actually being fabricated. Since the 1¼ inch thick web plates don't come from the mill in 14-foot depths to match the girder depth, the webs had to be spliced longitudinally. To make welding it easier, the longitudinal splice was straight. The camber was cut in the top and the bottom of the web plate. To facilitate shop drawing reviews and design checks, it was agreed that on April 4th, the web's shop drawings were acceptable, so all 15 of them were cut to size and spliced. While this is going on, the flange shop drawings were approved. To help speed up fabrication, all the holes for the flanges were pre-drilled on a CNC machine, then fit up to the web as you see in the far right photo. Since the camber was cut into the web, XKT used the jig in the photo and jacks to fit the flanges to the web so that welders could tack weld them into position. Once tack welded, they were stood up into position, as you can see in the two left photos. The top left photo, if you look closely, you can see simultaneous submerged arc welding machines being run to connect the flange on the bottom. Once this was finished, they would flip the girder and do the same thing on the other flange. Just so everybody knows, each length of the web flange weld took approximately 45 to 50 minutes. The vertical stiffeners were then welded to the web. All non-destructive testing was performed before the 246 web holes were drilled on one end. Using the web splice plates as a template, the remaining 246 were match drilled once camber was checked. Flange splice plates were also used as a drilling template once camber was checked. And just as a quantity for everybody to know, there were over 37,000 holes drilled during fabrication. Okay. So yes, this is a side view of the 4-inch thick bottom flange, the all-grade 54-inch thick bottom flange. Let me see. So just like the longitudinal, or just like the webs had to have a longitudinal splice, the bottom flanges were so thick that the mill could only make them in 30, 35-foot segments. So they had to actually do a horizontal splice on these. I'm going to actually go ahead and go through all these. So in this left photo, shows the worker beveling the edge to be spliced, while the middle photo shows the welding in process. Once welded, these were radiographically tested. Conventional ultrasonic testing also, as well as phased array ultrasonic testing, was performed for added quality assurance. There were no repairs needed for these welds. The first girder rolled out of the shop to the fit-up yard on May 10th, just 36 days after the first web plate was cut and just 2 months after the steel was ordered. Camber was checked with 3 adjoining segments, and remaining flange and web holes were match drilled. facilitate assembly and erection in the field, it was agreed to fabricate the first segment of each girder line first, then the second, and so on. Once the first 3 segments of each line were checked for camber and match drill, the first segment of each line was sent to the painter, R&B Coatings in Linden, California. Trial assembly was completed on June 21st, and the final 3 segments were shipped to the painter on July 24th. Paint used was polysiloxane, and the finish coat was applied in the shop. And the polysiloxane for this application was estimated to last between 60 and 100 years. And it was applied over inorganic zinc primer at the shop, and the first 3 segments arrived on site around July 28th, just 167 days after the column issue was discovered. And with that, I pass it on back to Neil.
Thank you, Jason. So real quick, I just want to go over some of our construction challenges in the field. As you know, this is a very scenic, windy, rural road, Highway 1 in between San Luis Obispo and Monterey. Wanted to point out, Mud Creek at this point had slid, closed. Paul Slide was another area. And then we had this little tiny road called Nascimento-Ferguson Road that connects 101 to the coast. And that actually, this route became very critical for getting materials and supplies to the site. Longest trailer length we could get on there is roughly 28 feet long. So, and we had some controlled convoys of material going back and forth on this road. This is Paul Slide. As you can see, the road is in, we had an active slide, and right through here is, I have an aerial photo coming up next, but a crib wall actually failed. Crib wall failed here. We're down to 1 lane. Mud Creek, this was a daily occurrence. They had to clear the road every single morning to allow, essentially the road was closed, but to allow construction traffic and Caltrans crews to get through to do their work. On May 20th, I believe it was, I said, here is actually the Mud Creek slide. As you can see here, this is Highway 1 to the north and to the south, and this added roughly 10 acres of new coastline to California. Site access was an issue, very narrow, constrained. This is the northern side, this is the southern side. We used about every square inch of real estate that we had. The canyon was very steep. The road we had to deal with, we had roughly about 30 to 40 feet in width to work with. We ended up staging the launching area to the north. Here's your abutment 2 support, temporary tower support in the middle here, and then abutment 1 support. Even though these are roughly 315 feet away, to get any equipment or anything from this side to this side was roughly a 6-hour drive, going all the way down, or going up to Monterey, down to San Luis Obispo, and back up the coast. Canyon access very steep. To the south, very steep slope, which was very stable. And then here's the active slide area with the famous column that was damaged. Here's a shot from the south side. We ended up using mobile concrete mixers, and all the supplies that needed to batch concrete was staged on the south side. And as you can see, very narrow work area to work in. Access from the north, same thing, very narrow. We can only do a few operations at a time just due to limited constraint. Here's some photos of the bridge demolition. Here's span 2 coming down, and its final resting spot, and span 1 coming down. At this point, I'd like to hand off to David Galarza.
Thank you, Neil. As far as our progression in the field, as of April 2017, as Neil indicated, the old bridge was down and the various pieces had been removed from the canyon. There was an existing utility line in the way. There was a communication line, but also a high power line that needed to get relocated. At this point, the structure design was complete, as well as the exploratory borings for abutments 1 and 2 and the temporary tower near the middle of the canyon. The steel shop drawings had been reviewed, as well as the welding quality control, paint quality work plans, and the steel plate had been ordered in fabrication and commenced. This is early April 2017. More importantly, we had selected a launch designer. At this point, the department had not performed this method in the past to longitudinally launch assembled steel plate girders. Additionally, we had hired an independent checker to check the launch designer's plan. The company selected was Somerset Engineering out of British Columbia. They had extensive experience in design of launch bridges as well as construction. Over the next several months, from April to July, we had focused on constructing the abutments on the north and the south. These are cast-in-place abutments supported on cast and drill hole pile, 5-foot diameter, approximately 80 feet deep. They were cast using the slurry displacement method, as there was still quite a bit of water in the surrounding hillside. We had also commenced work on the temporary tower. This is a prefabricated element on a step foundation. And this kind of gives you, this little animation gives you a graphic of the girders and how we had planned to assemble them in the field. Essentially, we're 3 girder lines. Each girder was broken down into 5 62-foot long segments for a total of about 310 feet. And each girder weighed approximately 60 tons, some were a little bit lighter than the others, especially as you got towards the end span. This short video shows delivery of the girders. These are coming out of Mare Island, which is approximately 200 miles north of the site, maybe a little bit further. These are about 60 tons each, and we'd bring them out in 3 segments at a time. They were offloaded from the trucks and then positioned on dunnage. The dunnage was graded to the camber of the webs to facilitate the splicing of the girders. He's erecting it into the vertical position and then moving the plate girder to mate with the adjacent girders preset. The launch plan developed by Somerset essentially was broken down into 5 distinct areas. The assembly area, which we saw the short video for, and then connected to the leading edge of that is a launch nose. The purpose of the launch nose is to collect the tendons doing the actual pulling of the girders and distribute them equally among each of the 3 girder lines. It's also there to extend the reach of the girders and act as a lightweight section. There are 3 temporary supports, 1 on each abutment and 1 near the middle of the canyon. And at the far end of the canyon on the left side of the page, there's a jacking frame that's housing the hydraulic strand jacks, actually doing the work, pulling the girders across the canyon. Somerset's design envisioned a 14-stage process. What we're showing here is stages 4 through 6. Because the temporary tower was very good at resisting vertical loads and not very good at resisting any horizontal loads, it became necessary to ensure that the nose of the launch nose rode up and over the rollers at the temporary tower. This was accomplished by lowering the girders in the assembly area, the temporary support in the assembly area, and thereby pivoting about the abutment 2 temporary support, raising the launch nose so it would ride up and over the rollers, as shown in stage 5. In a similar fashion, as the launch nose was approaching the southern abutment, stage 6 envisioned lowering the northern abutment temporary support, pivoting about the launch tower, and in a similar way, having the launch nose ride up and over the rollers at the southern abutment. Here's a good view. The right-hand slide shows a good view of the assembled girders. Here you can really see the soffit forms for the deck are installed. Additionally, you can see that we left an opening near the middle, and that was to facilitate removal of the launch tower once we were across the canyon. The left upper slide shows a good view of of the launch nose. You can see this is normally heavy, well, it is heavy steel section, but relative to the existing, the new plate girders, it actually seems pretty small. They believe these were W36 by 310 pounds. Here's some photos of the abutment temporary support. These are both at the northern abutment. And of note, on the right-hand slide, you can see that the two tendons coming in from across the canyon. That's what's actually performing the work to pull the assembled girders across the canyon. They're topped with a pair of 200-ton Hillman rollers, two 200-ton Hillman rollers, and there's some, at the top of the pipe supports, you notice a couple of 1'4" sections. Those are to be removed later so that we can adjust the trajectory of the launch. The temporary launch tower is a Waco tower, very efficient at carrying vertical loads. This tower was comprised of multiple 100 kip legs, but not very efficient at addressing any horizontal loads. So restraint was provided by some push-pull pipes. These are taking up any transverse loads and are founded on two CIDH piles. At the top of the tower, it's connected to a grillage that houses the assembly rollers. In the longitudinal direction, each roller was restrained by two 3/4" wire ropes that are cast into the abutment face. As you can see, those wire ropes are going directly to the rollers so that as loads are induced or as displacements want to be induced into the tower, they're picked up immediately and dragged back to the abutment face. On the far side of the canyon is the jacking frame. The jacking frame is also made up of heavy steel section and bolted directly to the top of the end of the wing wall. The wing walls are prop supported on 36-inch CIDH cast and drill hole pile, and so there's deep foundations that the loads will be directly braced to. There are two hydraulic jacks. These strand jacks are 235 kip capacity. Somerset calculated that he needed 110 tons of force to pull the girders across the canyon. Now, he purposefully designed these to have double the capacity that was needed in case one of these needed to get repaired or there was a malfunction. The remaining jack could hold the entire assembly in place. Both strand jacks were connected and synchronized by an operator. You can see from the lower slide, there's a power pack in between them. The operator had the ability to stop the launch and resync up in case one of the strand jacks got offline as far as load. In our schedule, we had allocated 3 days for launching, and we essentially accomplished that. It went off very well. There was very few incidents as we came across. I'd like to point out that lower slide. As we're adjusting the trajectory there, you can see the bottom flange just riding up and over one of the Hillman rollers on the south side. So as that launch progresses and as the girder extends out and displaces down, it's going to make contact with those rollers. It's a short video, time lapse of the hydraulic jacks working. You're looking at the left jack right now. The right jack is progressing similar. This is about an 18-inch stroke. For those of you familiar with stressing post-tension bridges, this is very similar. This is an all-encompassing unit, so it's got a stressing head, and it's got some relieving wedges that go ahead and grab and hold the system in place once it's cycling back. As the launch was progressing, we got slightly out of horizontal alignment. As you can see from the center slide, the center line of the web doesn't correspond with the center line of the assembly roller. The contractor made an attempt to correct the horizontal alignment by installing shims between the horizontal guide roller and the edge of the flange, and thereby wanting to rotate about the intermediate temporary support. There was limited success in this. We primarily did our trajectory and horizontal alignments during the jack down phase. There's a short time lapse on the right-hand side. This is actually lowering to do our nose up over the roller. There, you can see the stool is laying on the abutment seat there, and we're lowering our final 1'4" section so the nose could gently ride on top of the roller. It was vitally important that we perform monitoring of the launch while it was happening. To do this, we set up a total station and operator along the hillside, and he had multiple targets on the launch nose and on the grillage atop the tower to ensure that not only the tower wasn't exceeding its maximum displacement, but we were meeting the targets that we had envisioned when performing the trajectory adjustment. And since we're on a straight alignment, it was easy enough for us to set up a theodolite and operator further down station and just check the center line of the pole as we pulled across. He was in radio communication with the total station operator so that they're ensuring that they're seeing the same things. And as an additional redundancy, we placed some plumb bobs on the tower and just manually monitored displacement from there. I think our maximum allowed displacement was 1 3/4 inch for a tower that was approximately 75 feet tall. And I think we slightly exceeded that, but by then we were across the canyon. The jack down phase of the project on the launch plan was a 2-day affair in 2 stages, and we wound up actually taking about 2 weeks to perform this work. As you can see from the picture, the first step that we need to do here is to, here you can see that all 3 girders are actually supported on three supports, the launch tower in the middle and both abutments. So in order to lower these down to the abutment seat, we'd actually need to raise up all 3 girders and unload the center tower and disassemble it and fly it through the gap in the soffit forms that's connected to the girders. So here you can see a view of the load transfer from the 3 temporary supports to a cribbing stack. The cribbing stack is approximately 16 to 18 feet tall, comprised of 12 by 12 timbers, and the load essentially was transferred. These 3 pipe supports were removed, transferred to the cribbing stack, and the plan here is to cycle back and forth between the cribs and the hydraulic jacks, lowering 1 foot at a time on each abutment, and essentially seesaw all the girders down in place. You can also see that there's, above the cribbing stack, there's a temporary jack down frame that was there to facilitate it coming down and was removed prior to casting the abutment end diaphragms. As the work was progressing, we started to lower the bridge and got offline longitudinally, and that had the effect of walking the jacks off the center line of the cribbing stack. You can see there's a gap that's developing between the abutment back wall and the back of the cribbing stack, which caused us quite a bit of concern. The contractor was able to stop and essentially reposition the girders longitudinally using the rollers. And actually the next slide has a very good time lapse. This time lapse was provided by Mr. Kyle Evans. He's a local Big Sur photographer and was kind enough to let us use this for this presentation. So there the rollers are placed on the cribbing stack, and we actually used a small jack to reposition. Now we're centered between the 2 abutments. In the next step here, he will reposition the rollers 90 degrees so that we can get our horizontal alignment adjusted as well. During this time frame, we were experiencing heat wave. Usually down the Big Sur coast, it's pretty mild. At this point, I think we were exceeding 102, 106 degrees. So walking back and forth across the canyon from abutment to abutment sticks in my memory. So here he's, why don't you back that up for a second? So here he's repositioning the rollers 90 degrees. Oh, I'm sorry, I think that's restarted the video. So there he's got his alignment again longitudinally. Forward a little bit. What I wanted to show here was horizontal alignment push. Go ahead. There it goes. And then the final cycle. So there he's repositioning, he's stabilizing, doing his horizontal alignment. And then the final cycle was just a sequence of jack down. You can see him removing the upper cribbings here in just a minute, resetting the jacks, and then removing the top 4 cribs to lower down. There he's removing cribs, jacks will be extended. Remove those 12 buys and then lower down. And that was our 12-inch jack down. And then we'd walk to the other side of the canyon and lower that down 12 inches. We made it down to the abutment seat. The Eagle had landed. And at that point, we were into our conventional methods of plywood decking, completing the Nelson studs, our reinforcement, and our deck pour. We chose to do a night deck pour. The concrete that we used was normal weight concrete, approximately 550 yards for the deck and the southern approach slab. And then on October 13th, the bridge was functionally complete. There was a fairly large opening ceremony, and traffic was on it and restored to public service on the afternoon of the 13th. I believe it was Friday the 13th.
Yep.
At the completion of the job, there were several awards, multiple internal Caltrans awards, as well as local Monterey Transportation Agency awards. We were nominated for an AASHTO award, and I believe 2 American Public Works Association awards. And as kind of the majority of the team, obviously it was a much larger team supporting this team, but many thanks to Golden State Bridge, XKT Engineering, and Somerset Design, as well as Kyle Evans Photography.
This is Neil once again. So this will conclude our presentation of the Pfeiffer Canyon Bridge. As we're discussing questions and stuff, I'll play a short time lapse of the actual launch.
And that officially concludes our presentation.
All right. Thank you. Thank you for an excellent presentation. Certainly very much worthy of all those national awards that you have received. At this point, I'll turn it to Paul Lyles, who will moderate the question and answer period.
Okay. Y'all, that was very, very interesting project. We've got a number of questions that came in beforehand, and then some that have come in during the presentation. So we'll get into those in just a second. We've got them broken down into groups of construction and management, and then lessons learned, and cost, and then design. So with that, we'll go ahead and start with construction and management. And a question came in, or a comment said a summary presentation on claim handling would be interesting and beneficial to those considering ABC. Did you have any claims at all on the project?
Well, it was an emergency project at force account, but no, there were no claims. All costs were handled directly as billed.
Okay, that's usually what it is with emergency, so that's good. Then, were there any impacts to the project schedule due to the environmental permits?
You know, surprisingly for an emergency job, there were permits that were required from Coastal Commission, the California Coastal Commission, as well as Fish and Wildlife. But effectively, they wound up deferring all mitigation until after the project was complete. So there's a subsequent project that's dealing with some additional planting and relocation of utilities, so they're not a visual obstruction. So it did not affect the schedule during the course of the job, but once the job was completed, we're responsible to comply with the permits afterwards.
But we did, to clarify, we did procure emergency permits from the permitting agencies. So permits we got them in hand.
Okay. Then there was a project, now this came in beforehand. The question was the project essentially design build? and if not, were contractors part of the decision-making process for the method selected? It was not design build. You mentioned that. It was basically y'all picked Golden State contractors. How did you pick them?
That's a company that we had worked with previously on multiple challenging jobs via emergency and on a contract basis. And I think their approach to using innovative ideas to solve difficult construction problems really stuck out in our minds as a collective. It was a pretty easy decision for us.
Yeah, in addition to they're very familiar with this location. They've completed 2 projects in this area south of here, Pitkins Curve, which had a rock shed and segmental bridge. And then to the north, we had another problematic area called Rocky Creek, and that was another type of emergency project as well. So they're very versed in this location and know the challenges of the location. And in addition, they're able to complete these complex projects.
Okay, and then
I would say, I'm sorry to cut you off. I would say their input during the launch design and fabrication was valuable. A lot of the information that they had to help us with understanding fabrication of all the temporary launch pieces and how everything fits and goes together was instrumental.
Now that's fine. And then y'all supplied the plans were done in-house, and then it was force account for the contract. And then you showed how you did the steel selecting. Was the steel ordered and everything? Was that with the contractor was doing it? Or did y'all, once you picked them and said, this is the fabricator we want, who was the steel contractor? Yeah. Correct.
Everything was we provided direction, and the contractor, the prime contractor, Golden State Bridge, was in control of the order.
All right, that's good. Now, there was a question here about comparing and contrasting the advantages of planning versus reacting on an ABC bridge. This is an emergency, and that's usually where you're reacting. Planning, you can plan it and then close the bridge just for a little while you fix it. I don't know if you want to comment on that at all.
Oh gosh, I mean,
we basically made the decisions that we made with the most information we had available to us at the time.
And we did have weekly meetings too, right? The PM actually had meetings.
Correct. Yeah, through the life of the project, right at the very beginning of this incident, multiple meetings and people were brought together, and we ended up having weekly PDT or project development team meetings and also status meetings, and it was, we basically went through the progress of it. But as far as being reactionary, it was more, we had to make a decision. We had to get this bridge open as soon as possible because we knew the bridge was going to be closed for a certain duration. And so knowing that there was a landslide there moving, we didn't know what to stabilize. We chose the direction that we went based on the information we had.
Neil, this is Dory Mellon. I think when you look at reaction versus proactive, one of the things that really stands out is when you are planning one of these projects, then you can take your time during the planning. So you have more time for the design and procurement, and then you can control your closure. So if that had been the case, we probably would have gone with the hybrid 70 and 50 KSI steel option. It was more efficient, and the designer's here, he can speak to that. But because the driving force when you have no access, this community was basically an island, you go with the fastest alternative, maybe not the most elegant, and so we went with the 50 KSI.
It was real impressive what you've done. It was good. We had a question here about, go on.
I'm sorry. If we were to plan this project, let's say this facility had reached the end of its life and we were planning a new bridge, I think we go through the permitting process and the normal vetting that a project along Highway 1 takes. That would probably be, a 5-year process, and then leaving one lane open, building the bridge in stages that could easily add another 2 to 3 years of work in the field. So eight years potentially versus 8 months with the road closed.
Oh, that's good point. Okay. how did you manage this supply chain of challenges? What were the key success factors from a supply chain perspective? And I think you talked a whole lot about how you did the steel and everything. And was there any other thing you wanted to point out at all?
I think access from the south was really our limiting factor with the slides that we were having, and we just had a small forest road with which to get all the supplies, rebar, all the materials needed to cast an abutment, install temporary support on the south, and with essentially reach out to the local community and inform them, hey, we're using your single road here so that we can get this material in. So our public information officers, local media outlets, were able to communicate with them. And of course, we tapped additional assets with the Highway Patrol to help us facilitate convoys through that small road. So I think really southern access was the most challenging, getting that southern abutment complete and getting material to that site.
Do you have any problem getting your concrete in or your drill rigs in?
Yeah, so interesting story on that. So May 5th is when Mud Creek was permanently closed, and we actually had a convoy of about 13 to 15 trucks, including a 9-axle truck with the drill rig coming from the south. And those were the last trucks to ever traverse Mud Creek, because that afternoon they closed down Mud Creek, and we actually had to drop all the trailers and go over that narrow Nosmiano-Ferguson road. So that was a pivotal point in the project, getting that large piece of equipment, the drill rig across, and also the crane. If we could, we'd probably, really, I don't even know how to answer that question if that road was, if the slide happened before we got the equipment across, it'd be a different story today.
Okay.
And as far as the concrete and stuff, so to the north, we had ready-mix trucks. All that stuff was done normal process. On the southern part, we had mobile batch plants. We actually had one main one and then another mobile mixer on standby in case the main one broke down. And then all the concrete material was stored to the south and brought over on trucks as well.
Okay. Let's go to lessons learned a little bit. There was a general question about any lessons learned from the project. Any critical thing you'd take away from it?
Oh, I think for my perspective, it would be maybe not have a cribbing stack 18 feet tall with 900 tons atop it. That was very nerve-wracking.
Mm-hmm.
So if there was an alternate system that we could have used, we probably would have looked at that.
Yeah, another lesson learned, not necessarily an engineering lessons learned, but it was more of how this project went and how such media attention. This was a very high-profile project for our area, and there was a lot of curious people. They actually had weekly meetings with the local senators of the area, and they're demanding schedules when's the bridge going to be open. And then David here was a local star by the numerous news interviews he had to do, and there was a lot of attention to the demolition and the launching process. So we learned to manage our phrases, right? When we said launch, I had to be very specific. It's not like a rocket launch. It's a term we use to move, the bridge across the canyon. And then once, also for the demolition process, we probably had 13 media outlets, I believe, out on site. So managing the media on this type of high-profile project was definitely lessons learned.
Okay. Was there a question that came in about any ideas or lessons learned possibly about being able to predict this type of an emergency?
Yeah, this emergency was the first we've seen, actually a landslide displacing a column. I've never seen it in my career, and talking to others, they've never seen it as well. So it's really hard to prepare for this. But I think we reacted very well as a team within Caltrans here on just, the initial incident to handling the media and also getting the proper people in place to make this project a success.
And managing public safety, I mean, that was a priority, so.
That was very interesting.
You also have to consider the location. It's right on the Pacific Ocean. It's beautiful, but also the reason it's so beautiful is that it's constantly changing, whether it's erosion from, torrential rains or big storms throwing waves up against the rocks, undermining from down below. I mean, the potential along that road is there.
Okay. The cost, look at some cost questions. You gave a cost total at $21.7 million for the total cost of the project. Would you want to say anything about the cost comparison between an emergency project and a normal project?
Well, I think if this was a normal project and we took, let's just say, 8 years to do it, and we could also assume we took 8 months to do it, and we assumed maybe a 1-to-1 comparison of cost versus time. So you could take our $21.7 million and multiply it by the appropriate factor, and I don't think it would be in the hundreds of million, but it certainly would exceed 50 million.
I think okay. what we've experienced with these kind of projects is our capital outlay on the bridge cost may be higher than the bridge cost estimate, although we did have a lot of efficiencies by getting to do this with a full closure, whether we wanted it or not. But the reality is you save a ton on administrative costs and the permitting process and all that goes in it. So nobody wants these things to happen, but there are some efficiencies that we experience when we're pushed to do it quickly, and we can kind of wait and do the mitigation and the other issues after the bridge is complete.
Okay. Did you have any feeling at all for any additional costs associated with the launching versus crane setting?
I think crane setting really wasn't, and we discussed it, conventionally setting girders, but because there'd be temporary towers in an active slide, and we potentially have to build a trestle with a very large crane, a trestle that could support maybe a crane on the order of 600 tons. It really wasn't an option for us. So the last thing we want to do in an emergency is try something new. We want to go with our gut is to go with our standard tried and true practices, but in this case we had no option.
Okay. Was the bridge fracture critical?
No.
Okay. Then on the foundations, please comment on the conception and construction, the new foundations. You talked that you showed them the shafts at the indents. Did you use the old foundations at all, even as an abutment? Did you leave anything in there, or were they completely removed?
No, they were fully removed, and the existing abutments were actually on spread footing.
Okay.
I will say on the southern abutment, one of the existing wing walls was, because the new alignment was straight relative to the old alignment, the existing wing wall acted as really good shoring, and we left it in there for a significant amount of time until the new abutment was cast, and then removed it in place. But as Neil said, all the existing abutments were removed. There were not any conflicts with the pile shafts. Were a simple span across all those existing elements.
Okay, that's the earlier questions. So Torrid, you want to take it from here and ask some of the questions that have come in during the session?
All right, thank you, Paul. We have received several questions. I don't believe we are going to have a time to ask all the questions, but I will try to touch on a couple of them that will complement what Paul asked. The one easy one, was the project federally funded?
We did apply for reimbursement from the feds, and I think last I heard we were going to get a 75% reimbursement of the 21.7 that was spent, and then the balance of the money between the 24 and the 21.7 went back into the state highway emergency shop fund to fund other emergencies across the state, of which that year we had a lot.
Okay, great. Also, there's one question that came in that is asking that basically, why did you select the steel bridge? steel as a material? Was the because of the speed of construction cost, or the fact that you wanted to use a form of ABC in the form of a lunch?
I think if we went with another material such as cast-in-place concrete, which were post-tension cast-in-place concrete, which we're very accustomed to and familiar with here in California, I think because of the false work that would be required, it may have been prohibitive because of the slide.
It's lighter than steel.
And steel's much lighter. It's much easier to launch than a concrete element would be.
Okay, great, thanks. One last question, probably this will be we have a chance to ask one more question. Again, we have received more than 16, 17 questions, but we'll try to answer the ones that we don't have a time to ask later on and post on the website. The last question is that even though you showed the method of the demolition, there's a question that came in that is asking, can you please explain the initial demolition plan for the bridge where the wrecking ball was being dropped onto the deck, and how was that plan developed, and are there any good lessons learned from that?
Yeah, the initial demolition plan was to use a wrecking ball. The reason why we did that because we didn't want any personnel on the bridge itself due to its unstable state. So they tried to come up with a plan to use the reach of the crane and get out there, and they had a strategic plan to kind of massage or crack up the bridge deck and key locations where you could see where the bridge was failing, and hopefully maybe accelerate the bridge in its falling. We had some mechanical issues with the crane. It wasn't working. So essentially they had to reconfigure the crane to get the crane to work, and we did actually end up using the wrecking ball. I think it was roughly on day 3 after all the bugs were worked out. And they were able, unfortunately, since we reconfigured the crane, the reach was not as far as we wanted it to be, so we could only really get to roughly span 2. They used the wrecking ball to break through the deck, and then after the bridge essentially bound up on itself, it wouldn't move anymore. And so after that, we would just went with traditional methods as far as using excavators with hoe rams, and we demoed each span that way.
Oh, fantastic. Again, on that note, we are going to end the webinar. Thank you for an excellent project, an excellent presentation. And again, on that note, we are going to end the webinar, and we hope everyone join us for our May webinar. So long.
Thank you.